Next talk is by Dr. Dmitry Onishchenko from Gazprom, Moscow.
Yes.
And the title is Probabilistic Aspects of Multi-Element Systems Failure. So,
okay, well, thank you for presentation of myself. First of all, of course, I would like to say thank you very much to the organizers of this symposium for inviting to participate here, because there is a lot of people who have a lot of very interesting results in ice mechanics in relevant situations. A number of them I am familiar for a long time, and this is very nice to see them personally here. And of course, I would like to appreciate the hospitality of the administration of the Newton Institution for, again, for the possibility to participate and to enjoy listening to other specialists and so on. Okay, I am very happy, first of all, to give a presentation because my primary interests for many years is the probability, applied probability in connection with the reliability and safety of the structures, and here I have a possibility to say about several topics which I dealt with during many years ago, and some of them, but not of all, are connected with problems concerning ice loads and designing structures in ice conditions. So mainly my presentation will include three more or less separate parts. Anyway, I hope that any of them could be of some interest in some aspects. Anyway, all of them mostly are connected to my participation in the examination of the ISO 19906. This is international standard devoted to Arctic offshore structures designing. A very huge and very informative document. A number of very different issues are included, and some of them are questionable from my point of view, and I will talk about this, and in parallel will present some results concerning these areas. So at the beginning, some general idea concerning random nature of ice loads. Then I will present rather simple model of fragmented failure of level ice and some results following from it. Then we will talk a little about the area named structural reliability, and I will show rather simple but anyway I think possibly useful model which can describe some processes as for structures progressive failure, as well ice failure through which we can deduce ice loads on a structure. And finally, I will talk a little about these two parts are connected with modeling, with dealing with multi-element systems. We will have a system consisting of a number of elements, and the last one devoted to possible approach to iceberg threads for platform is not in fact multi-element system. However, if we can consider the sequences of incoming iceberg like a system, then anyway this could be multi-element system as well. So motivation, I said about this, ISO 19906. Some definitions for those who are not closely involved. The main target, reliability target for designing offshore structures, is formulated in such a manner. reliability target. This is a specified average annual reliability associated with avoiding failure. Okay, I do not like at all this definition. In fact, I think it should be that reliability target is the probability of not to be failed for the structure, and that's all. The word average annual probability is not understandable at all, and so on. Well, it's easy to criticize, but anyway, we should be careful with formulations in the codes suitable for designing structures. And two basic notion. The representative value of extreme level ice load or ice section shall be determined on an annual probability of exceedance not greater than 10 minus 2, and the so-called abnormal level ice load should be taken at the exceedance level not greater than 10 minus 4. I wanted to reformulate. So, for instance, the abnormal load at the with a representative value. This should be such a quantity Q star, for instance, that the probability to obtain the ice load greater than this Q star during 1 year, yeah, it should be not greater than 10 minus 4. So this should be the quantity at the very right tail of the distribution, yearly loads of ice sections and so on. We have a jointly connected notion return period. This is the statistical notion, very simple. This is the average period between occurrences of an event or of a particular value being exceeded. That is, if we deal with that quantity Q star, about which I said before, then the average period between exceeding this Q star expressed in years should be 10 to 4. So return period by definition is reciprocal to the exceedance level, and that's all. And here I would like to add that I think it's not correct to think about this period, for instance, 10,000 years, as we should know or imagine what will be the ice conditions during this huge period. No, we should think about ice load in this term. So we should use the current climate information and try to estimate this quantity through the distribution function. I think all understand clearly, including the previous presentation, that ice strength is a random quantity, and without probability it's nothing to do. So we realize that like local ice strengths, similar the global load should be considered like random quantities, and we need to construct suitable models for these features. I think again all knows the internal and external factors due to which ice loads and ice strengths is a random value, but I would like to pay attention that I think the most influencing factor for randomness is that ice load, to the contrary to other environmental load, is a result of the failure of the ice. All other environmental loads are not connected with failures. Ice is, and the fracture processes is very stochastically changeable, and this is the main reason why ice loads and ice strength is random at different scales. Okay, then we go to the general definition of designing. Again, very short introduction. We need to hold so-called design equations or criterion for a number of design situations. For instance, in application to gravity-based or pilot-based structure, for which we have horizontal ice loads, we need to adjust this very simple inequality. The horizontal force should be less than the resistance of the structure due to horizontal motion. It's very simple in such annotation, but all we understand that we have a whole set of such inequalities, because the load is not one parameter, resistance is not one parameter. For instance, in application to soil mechanics, we have the so-called envelope for the stability of the structure at the bottom. Then for pilot structures, we have another number of criteria and so on. Anyway, for me here is important that a designer in principle is dealing with deterministic formula, with deterministic equation, but all probability is where, of course, in the design resistance and in the design loads. Here we should have a probability, but recent practice and the last intention of some authors of the code is to raise probability to the next level, and sometimes I met the ideas to express the design criteria in a probability manner. That is, the designer should provide such a design that the probability that, for instance, design load or maximal load due 1 year could be larger than the resistance is at the level 10 minus 4 or similar 10 minus 2, I'm sorry, the same, it's a mixture, and so on. I think that it's very bad thing when we are trying to involve designers of structural features to deal with probability. I think we need to deal with probability only where we are trying to determine ice loads and resistances. Okay, I would like to present simple model for level as ice interaction with the structure. I think that you can easily imagine that this is in part similar to those models presented in other authors here. What is the idea? We understand that we have no simultaneous interaction of ice with the structure. We have several active zones. So idea was very simple. It's not my idea to present the whole ice sheet as a set of parallel lines. In the simplest case, we can consider this line separated by some boundaries, and so we will have a sequence of similar elements located on one after another in every such line. But we will consider the case when we have different phases, so different fragments are approaching the structure with some shift in time. So we introduce some null simultaneous approaching and acting of these elements on the structure. Okay, global force is the sum of not local force, but here I will say like local, understanding that local force is the force from each separate fragment giving to the structure. And so-called global effective pressure is the global force divided the area of contact. Then we introduce in our model the loading diagram, which is given to each of our fragments. We can introduce a number of loading diagrams. So here we have dependence of ice strength or ice force on the obstacle, independence on the indentation length u. For instance, this can be considered as crushing mode. This can be considered as mode responsible for bending fracture, and so on. We can add a number of others. If we have some special equality between parameters, we can obtain so-called continuous crushing diagram where we have such tools rather understandable. We will give probability for a given element to obtain one or another mode of failure. Another random variables will be strength of the element and maybe position quantity UC at which we have the maximal load from the element. For simplicity, we will use for the strength variable distribution with some specific parameter. It's not hard to write down the graphics of those loads. Then very simple consideration that the global effective pressure is the mean value of loads from fragments. Here sigma I is a random function, as I said. They are equally distributed, and due to well-known central limit theorem from the probability theory, we have that when n tends to the infinity, the global pressure is tending to some well-defined quantity, mathematical expectation of the strength related to one alone fragment. It's not a problem to calculate this, I will show. And anyway, in our very simple mode, we see that we are trying to model non-simultaneous failure like by the asynchronous approaching of fragments to the structure. We have this asynchronity at the very beginning of the process, and it will be sustained due the whole motion of the fragment of the ice sheet on the structure. A bit of mathematics, it's not very interesting. It's possible to calculate analytically this very simple quantities, and you see we have that mathematical expectation of strength of force from one fragment, which is again the mathematical expectation of global pressure, and we have such an equation. All initial parameters are here, probabilities PC, PB, the average value of each fragment strength, sigma C, due to variable distributions, and some additional geometrical parameters, the length of a fragment, and some critical points, and so on. What is important for me here, it's clearly followed from here that the mathematical expectation of the global pressure always is less than the average value of the strength going from one fragment. That is, in a sense, the global pressure should always be less than the local pressure, we can say in such a manner. When we have continuous crushing without additional parts of our diagram, we have this inequality. Global pressure is 1/2 of the pressure going from one fragment, and if all phases would be synchronous, yeah, definitely we would have that mathematical expectation of the global pressure would be exactly the same like going from one fragment. But the more interesting thing is to see what we will have when our ice sheet is going longer and longer against the structure, because definitely we have some kind of random processes. It's not a problem to complicate the model. I will say several only words that we can introduce the appearance of cracks, so the width of new fragments will be different. We can introduce the random lengths of these cracks and so on. And then we can use some simple code to program this and to obtain diagrams which I will show. For general vision, structure width 100 meters, ice thickness 1 meter for simplicity, mean crack distance 10 meters, that average width of fragments is 10 meters, average length again is 10 meters, but these are random quantities I said, and some specific figures for available distributions which give average strength from one fragment 3 MPa and standard deviation 1.5. Okay, here is diagrams obtained numerically from these simple models. By the way, they can be seen like rather realistic. Of course, the magnitudes mostly depend on the part of fragments crushing failed in crushing mode. This we have 0.5, this 0.2. Definitely, this graph is generally lower than that one. The most high load is for pure crushing, and here in another scale length, 10 kilometers, we have such graphs. What is very important here? Definitely, this is some kind of random process of Gaussian type, and it is well known that maximal values in such processes are increasing with the total length or total time of these processes. It's known that for Gaussian processes we have this kind of increasing, the square root from the logarithm of t. Here this can be clearly seen, this tendency. So it doesn't matter what figures we have. Very important is then that when we are considering the loads from rather simple ice feature like level ice, it seems that it's necessary to take into consideration not only probability features of strength of that ice, but the length of those ice which can go through the structure during 1 year. So this can be taken into account anyway, I think. Then next maybe interesting deduction, that when we have measured ice loads at separate panels on the wall of the structure, it's not straightforward to reconstruct the global ice section on the platform, because we can see that we can have very different situations, and how to take this into account, it's not clear completely. And of course, very big question is what should be the characteristic length of ice fragment L in our previous notation, which is most suitable for possible estimating ice loads in such simple models like I presented before. Okay, it's not very, it's interesting, but I have no time. I would like to refer to ISO 19906, where for design load from level ice section, we have these two simple formulas. First one is elementary, global ice pressure multiplied the area of contact, and for global pressure we have such an expression where CR is something similar to ice strength, local ice strength, so-called ice index, and again H is ice thickness and W is the width of the structure. For coefficients N and M we have some specific equations. It's not only me who tried to estimate these quantities, but anyway, it's very easy to check that we can change equation 2 by equation 3. We have here H multiplied W to the power M, and in the range of 0.5 to 4, maybe even to 5 meters, the difference will be not higher than 5%. So I can't understand why this formula is included in the document, and why not this one. If we try to use this formula and perform calculations to estimate the design load, we would obtain another not very good thing in ISO 19906. I omit details. The quantity at the exceedance level 10 minus 2 will be for this initial data which were used for that document in the so-called calibration procedure for the Barents Sea. So this quantity 10 minus 2 will be 145 meganewton. 10 minus 4 will be 161 meganewton. And what is a bad thing? That in the ISO for so-called extreme level load, I should use factor 1.35 applied to the value of the exceedance level 10 minus 2, and I will obtain immediately 196 meganewton, which is much higher than the so-called abnormal load. So not good situation, because for abnormal load I should perform a non-linear elastic plastic analysis and so on, and for extreme level load I should perform only elastic and linear analysis. So the philosophy is bad if we can refer to these inequalities. Okay, interesting question for me is it possible now to add some interaction between fragments in order to obtain some kind of synchronous manner of their impacts on the structure? Because currently I said we have different times of approaching the structure. Maybe it is possible. It would be very grateful if one could suppose some physical feature how to try to force these fragments to become simultaneously acting on the structure. Okay, it's the same. I am trying to adjust my time. Anyway, because we remember that the main target of designing is to obtain the reliable structure, we need to understand what can be with the structure under some load. So we should analyze the possible destroying of the structure, destroying element by element. I would like to show at the very simple example that this problem is highly difficult, and okay, some consequences will follow from this. If you consider a very simple model, 2 element or 2 column or 2 fibers loaded with joint load with mass m. Let us imagine that all these 2 elements are absolutely the same except their strengths. The strengths R1 and R2, and these quantities will be random quantities. Very simple question. Given these parameters, what is the probability for such a system to fail? I suspect that not everyone would be able to give answer to this equation, but this, in fact, this is not a simple problem, and I will show why. The devil, as usual, sits in the details. We don't know what we should do after one element will fail, because we can imagine that we are using a static approach, quasi-static approach. Maybe we can introduce some dynamic effects and so on. And depending on loading scheme that I can take rationally for this situation, I will obtain at the so-called, I will obtain different fail areas, because the answer to this question is an integral over known density functions of the strengths over some area omega, and this area omega will be different for different loading schemes. And this means that we have no one unique answer. We must to choose and to explain when we use one or another of them. In the simple case, I will give the answer for 2 elements. This formula we can check, where f naught is the distribution function for the strength of one element. In other cases, when we have rather more difficult areas for integration, the answer is not able, could not be able to be obtained in closed form. So, to deal with failure of multi-element systems is very thin matter, and so it's necessary to construct some special models. I'm sorry, I will omit this part of my talk. This is related to some general theory how to deal with multi-element systems, which has such interesting property. Systems with no unloading. Systems with no unloading are such systems where the force in any element does not decrease during progressive failure of the structure. It is possible to construct the whole theory. It's very interesting for me, but I'm sorry, I have no time for this. Maybe somewhat later I will show something this here. By the way, in 1945, British statistician Daniels found the complete solution, not 2-element system, but n fibers bundle, and he presented the closed solution and finds the asymptotic distributions and so on. But this result was during many years unknown to structural engineers, and even in 1983 and something near, I found some papers where it was written that it is possible to find the solution for 3 elements, but it's almost impossible to find for any higher anyway. And I think I have maybe 10 minutes, I ask for 10 minutes, to talk about another multi-element systems connected with the very important for some region problem, how to estimate rationally the danger of iceberg appearance in the area where we have whether fixed or floater platform set for development of one or another field. Such area very famous is of course Newfoundland Bank, where we have a lot, some of us have a lot of icebergs. For instance, average value per year in the square 1 degree over 1 degree is several hundreds, from 2 to 5. The maximum mean average about 1/200 per year. At the Stockman field in the Barents Sea, we have much more easy situation because the total number of observed iceberg in the place where it was planned to locate Stockman platform floater is only about 100, and so the intensity of incoming icebergs is much lower. Anyway, the problem is the same: how we can rationally estimate the risk of iceberg impact against the structure, because this could define the very concept of the platform at the place. What can be taken as the measures of ice risks? A number of them. First of all, the frequency of iceberg arrivals at the site, at a given area, for example. Then, the probability of iceberg impact against the structure during a year. Sometimes this is insufficient for design because this probability does not include information about possible iceberg size and velocity. Then another measure, kinetic energy of the iceberg impacting the structure. The most favorable might be the maximal horizontal force which an iceberg could give to the structure under the impact. But I do not like this quantity because this require very big amount of additional information about the geometry of the iceberg, about the pressure area contact dependency, and so on. Anyway, in ISO 19906, this danger event like impact of icebergs is included, and a designer should demonstrate the estimates of this danger for the designing structure. We know that icebergs have very twisted trajectories, and this is a model presentation. It's some examples of real iceberg, thanks to Alexei, which provided me with one or two of them. In ISO, we have some results concerning this problem. First of all, we have this equality. Nu is the rate of interaction per unit time, where rho A is the so-called spatial density of iceberg, that is the mean average, the mean number of icebergs in a given area taken at instant moment. D is the average value of diameter of incoming icebergs, W the width of the structure, and V bar the average value of incoming icebergs. Again, unfortunately, I badly adjust my time. I have no opportunity to give some details, but I will show that this equation sometimes is not right, as well other relations about which I will say further on. Then it is stated in ISO 19906 that the probability to impact the structure is given by such a formula where we have additional parameter T bar. This is the average value of iceberg being inside the given area, also called residence time. Sorry. And it is stated in ISO that when we are trying to estimate the danger to the structure from the impacting icebergs, we need to change the distribution for probability distributions for velocity and for diameters to another one due to bias approach and bias formulas. Again, this is questionable. I will show a little bit later on. I will take a very simple model again, where we can consider such a situation. All icebergs are arriving at this line, start line. The position is random quantity due to uniform distribution. Then each trajectory has a specific zigzag curvilinear form. We have so-called twisted factor, quite understandable. And the phase of incoming iceberg again is quantity S2, again is a random quantity. Let the diameter and velocity of icebergs be random quantities. Then very simple question: what is the probability for such sequences of icebergs to impact the structure during 1 year, when the intensity of arriving icebergs is taken as lambda? This task has a closed solution. I will show only that even in the most simple case, when we have trajectories like straight lines, so-called model of raindrops model, we will obtain a result that is not coincide with the formulas presented in the ISO 19906. By the way, it's very interesting to show that instead more or less usual V bar, average velocity, in our formulas obtained through quite simple calculation, we will use this rather specific quantity V bar, which is a reciprocal to the mathematical expectation of the reciprocal of the velocity. It's something similar, but of course not the same. And only using this quantity we could obtain some results. Here we have the result, the probability of arriving icebergs to impact the structure for any of them. Very similar to ISO, but except for this velocity quantity. But this is not all discrepancies, because in this simple model it is important to show that when we would like to modify the probability distributions of diameter and velocity of iceberg impacting the structure as compared to the icebergs arriving to the area, we could obtain that, yes, we should change the distribution of diameters, and this is clear because the larger is the diameter of an iceberg, the larger is the probability to impact the structure, because the trace is wider. But as for velocity, no, the distribution is the same. 2 minutes, please. Yeah, and the same picture will be for more refined model with this non-straight line trajectories. Again, we can obtain that we need to change the distribution of diameters. We need to change the distribution of this twist factor, but again, we need not and must not change the distribution of velocities of iceberg impacting the structure. And this is in contrast with ISO 19906. And so some conclusions. First of all, the possibility of joint modeling of structural liability and statistical variability of ice sections is rather questionable to a number of points about which I said, and so we need strictly separate the obtaining design loads and to perform structural analysis for platforms. Some requirements in ISO have to be checked and possibly corrected, and some general ideas from statisticians who have dealt with the statistics. It is stated that even slight variations in the model, accounting for mutual dependence of random variables or their marginal distributions, may often have dramatic consequences on the prediction of extremes. Definitely 10-2, 10-4, these are extremes quantities. And it seems that prediction of extremes is in general a risky field, so we should be very careful in our calculations and so on. Moreover, in ISO relevant ISO 19901 related to metocean design, it is clearly stated that we are not able to go far ahead. At least 25 years data set should be used to estimate 100-year storm parameters. How to deal with 10-4, it's not understandable at all. Sorry. How to check? Yeah, this one. And the last one, I'm sorry, yeah. One example how we need not write structural codes. This is not ISO. It was a lot of critic to that one. This is Russian document, and I would like to give this idea in order to understand. This is Russian federal law. That is, it is mandatory document for using in designing and in construction, so on. Technical specifications for structural safety. I try to translate in order all of us understand. Again, please. Structural constructions and their foundations shall possess such strength and stability that no threat of harm for health of people and environment and so on could arise during structure's life as a result of failure of the whole structure or any its part. So, if I understand this clearly and in straightforward manner, a designer is responsible to provide such a structure that in case of its failure, there was no any danger to people, to environment, and to economy, and so on, so on. Of course, this is the responsibility of authors of this document, but it is active and it is a mandatory document in Russia, and it has such very bad formulations. So I would like to add that now ISO 19906, which is very important document for designing offshore structure, it is under active expertise in the world, and if someone is interested or has or is relevant to this document, please let us all expertise and give our remarks to improve this document, because it is very important. Thank you very much. I am very sorry to enlarge my presentation. Thank you. That's all.
Thank you very much.
Thank you.
We have time for questions. Yes, please.
This is very interesting, and just throw out the notion that if we had to design cars like this, we'd all be driving tanks.
Yeah. Good. For which exceedance level?
There's a question here.
Well, your talk suggests many questions, and I'd just like to ask one. You referred to the ice pressure formula in ISO 19906. I must say my personal view is that that formula has such a dubious basis that it shouldn't be used at all. But you've clearly come to a different conclusion, and I wonder if you could tell us about that.
Yeah, I'm sorry. I'm afraid I didn't catch the whole idea. Yeah.
I didn't understand myself.
Do you say about ISO formula?
Yep.
ISO formula,
Yeah,
ice pressure. And what is the question? I take is as it is and check that I can change it.
Well, indeed, but why did you take it as it is? I regard it as having no value.
I don't understand
Okay,
what is
so
no right value.
Эта формула плохая, ее не надо использовать.
Yeah, so because, well, I definitely, in that form to which I reduce the initial formula, it was proposed about maybe 20-30 years ago, and it was shown that it is bad form for such a presentation. But anyway, it is included. I don't want to to discuss whether it's bad or no.
Can we see
What-
what formula you are talking
Yeah, but definitely. But I think that this is responsibility for those who produced a lot of experiments and so on. But you see, this formula, which is very in figures, very similar to this one. It was proposed a huge number years ago, and I have written that this formula was bad. But now, after some years, we come to the same equations. But this is the equation to the authors and to the management of ISO 19906.
So if you think it's bad,
Yeah.
why do you use it? Why do you mention it? Why do you take on?
I myself do not use it, and moreover, in Russia, this document is not active still. And now we are considering this document, and I do not know in which manner Russia will vote or against this document.
Okay, we can stop that discussion. We can continue in the break. Any other questions? Some other comments, maybe? Sasha? Alexei?
Yeah, I think this topic about iceberg drift and collisions is quite useful for the demonstrations. It's simple and included in exam for my course each year. Then, so last problem.
Yeah, I'm sorry.
If you may comment more around that, because
Yeah. Yeah, I'm sorry. I definitely made a mistake. You put too much information. As for icebergs, several words, if possible. Anyway, it is some ideas about modeling of iceberg threats in ISO. I said about this. And there are some general statements. For instance, icebergs having larger diameters and more high speeds are more likely to impact the structure. As for diameters, for instance, this is right, but this is not right for velocities. And I know I could understand why this was chosen. Just a moment. Because authors of ISO, they take the average value of residence time, and then due to this residence time and larger velocity, definitely the length of the iceberg path, which should be inside the area, is larger than the path for those icebergs having smaller velocity, only due the fact that they took fixed residence time. This is wrong. Of course, faster icebergs, I suppose, yeah, have smaller residence time, and this is the mistake in these considerations. And I would like to show on that simple models why this is wrong. And again, this formula, which again in ISO it is stated that a designer should use this modification to velocity distributions. Again, this could not be considered as absolute truth. Sorry. Yeah. Okay.
I think it would be useful just to take trajectory and ice tracker, deploy it on iceberg, and demonstrate that it's wrong.
Yeah, you see, I have written, yeah, we need a model describing iceberg's motion within the area in question. The authors did not use any model of motion of icebergs inside the structure. They use pure geometrical approach and so on, so on.
Okay, I think, well, the time is up. I think we have tea. Thank you once again.
Thank you.